I think most of you guys are back. I want you guys to do me a favor whenever we have a meeting. When we break off and come back, please tell me, Prof, are you recording? Because the recording stops and I'm supposed to put the recording on again when I come back. And the last session I forgot, so that means I've got a huge hole in between my first recording and the last recording session because we had 3 40-minute sessions. So this whole recording has been spoiled. Please help me along. So whenever you come back and say, please record, Prof, before you start. Right? Okay, Sarah, you had that. All right, now we're getting into problem number 15. A square tile is divided into 4 smaller squares. I want to read through this problem as shown. So you got these 4. The square tile is divided into 4 smaller squares. Right. Each small square must be painted using the letters yellow, red, or orange, or blue. So you got yellow, red, and blue. So you got 3 colors. You're painting this tile here. So how many different tiles can be painted if exactly 2 colors are used? So you want to use only 2 colors. And how many ways can you paint this tile? So if I've got 2 colors, I can have red and yellow, yellow and red, or whatever it is. And you want to know how many different ways can you paint it. Now, by different, it means that no matter if I rotate the tile, right, it must be yeah, if you rotate it, it mustn't come back to the same thing, right? So let's have a look at this problem. You were using 2 colors to paint these 4 tiles. Let's see how many ways can you do that. So I got a nice picture here. So what I'm saying, let's fix 2 colors, yellow and red. Now, how many different tiles have you got? Now, I've got the answer here. So you must use both the colors. You can't use just one color. You must use 2 colors. All right. Now, the way of doing it is actually, if you want to be systematic about it, so you start by saying, let's look at, suppose we say we use only 1 red. Now, if I use 1 red, I am now looking at this part here, right? This part here, 1 red, then it'll be 3 yellows. But you might say, okay, this is not, I could have made this as 1 red, other 3 yellows, that has 1 red, other 3 yellows, that has 1 red, the other 3 yellows. But if you think about that, it's the same tile. It's no different. Because all you have to do is to just turn this thing around, in different ways, in different directions, clockwise, anti-clockwise, and you will come to each one of these situations. So there is only 1 tile with 1 red. I hope you understand that. There's only 1 tile. If you turn it around, right, you can get different positions for the red, but it's the same coloring, right? So you've got 1 red is like that. Now, you could have had 2 reds. Now here, there's 2 reds. You could put 2 reds here, in which case these become 2 yellows. But now watch, 2 reds is like this. And 2 yellows. These 2 are not the same. You can see they're clearly different, right? But mind you, if I had 2 reds here and 2 yellows here, it's the same as this. Because if I turn it around, I can get, if I turn this thing through 90 degrees in a clockwise direction, you'll get 2 reds here and 2 yellows. So that is no different from this. So there's only one tile having this configuration, and here too there's only one tile having this configuration. This is no different from having red, red, yellow, yellow, like that. It's the same thing. Right? So, and finally, if you got 3 reds, it'll be like this. Right? So you can have 1 red, 2 reds, or 3 reds. We are systematically counting. You see, we know we're going to use 2 colors, and you must use both the colors. So you can't have 0 reds. That's not allowed. But you can have 1 red. You count that. You can't have 2 reds. You count that. You count 3 reds. You count that. You're not allowed to have 4 reds, right? Because then you don't have any yellows. So these are only 3 possibilities. And for each one of them, you count that. You got 1 plus 2 plus 1, because you got 1 in the 1 case and 1 in the 3 case, but 2 in the 2 case. So you got 4 such tiles. Right. So that is when you got yellow and red. But now you got 3 different colors. So we chose YR, which is yellow and red. You could have chosen, what is T? Oh, this is supposed to be Y here. Okay, you could have a YR and YB, yellow and blue. Oh no, I've got that. Yellow and red. What's the next one? Oh yes, red and blue. I could have had red and blue and BY. So this is supposed to be red. I must correct that some other time. Okay, so therefore, there are 3 possibilities there. Each one has got 4 configurations, and altogether there are 12 types of tiles. Okay. How are you guys? Are you happy with the last problem? Yeah. Okay, Kristen, I see you got your thumbs up there. Okay. All right, Sutirtra, Edward, right, okay. So that is counting tile coloring. Now let's go on to the next problem. I think we're going to number 15 now. All right, what is the remainder when this object x to the power of 52 plus 201x over x is divided by x plus 1? Now, I don't know why they did it like this. This is rather silly. The x cancels straight away, so you could say this is x in x to the power of 51 plus 201. So we rather work with x to the power of 51 plus 201. All right, now this is quite a new problem. What is the remainder? You got x to the power of 51 plus 201. Now you can divide. You did learn how to divide one polynomial. You call it a polynomial, x to the 51 plus 1, divided by x plus 1. Long division, x goes into x to the 51, x to the 50 times, and you keep working like that. But you know, you got 51, the index is 51. It'll take a long time before you can get to the remainder. Right? The remainder will be at the last term. Right? So you can appreciate this can be a very horrendous problem if you did it in the normal way by dividing x to the power of 51 by plus 201 by x plus 1. So you'll have a huge quotient. It'll take you a long time before you can get to this. So I'm going to give you some prerequisites to this. I'm going to give you a talk now about polynomials. Right. I've got a big screen here, and we're going to focus on different things at different times. Let's go to this top corner here. Let's talk about polynomials. What do you mean by a polynomial? A polynomial is like a flat expression, like that. I call it a flat expression. You're not dividing by another polynomial or whatever, like this. This is a polynomial. This is a polynomial. And here you got 6x to the power of 7 minus 15x cubed plus 3x squared minus 8. This thing here is what you are familiar with, is called a trinomial, right? 2x squared plus 5x plus 8, or whatever, if you put numbers to a, b, and c. But the correct word for it will be a quadratic. It's called a quadratic polynomial. So it's a quadratic polynomial. The polynomials with the exponent 2 as the highest exponent are called quadratic polynomials. And if the highest exponent was 3, you call it a cubic polynomial. But those are the only ones you call it quadratic or cubic. The other ones you don't give any names to. Like this one here, you will say it's a polynomial, but you will say it's got degree 7. The highest exponent is called the degree. So this thing here has got degree 2, and this has got degree 7. And this is a polynomial which has got degree 51, the one that which is under investigation. It's a polynomial of degree 51, but most of the terms are missing. See here, you got the other terms are still alive, but most of the other coefficients are 0 here, right? But it's still a polynomial because it's looking very much like that, but a lot of coefficients are 0. The first coefficient is 1, and the constant term is 201. Okay, so those are polynomials. Now, there is a very nice theorem which tells you how to find the remainder when you are dividing any polynomial. Look, let a be any number. Now you take any polynomial, we're giving it a name, we're calling it f of x. So this could be f of x, that could be f of x, that could be f of x. All these are polynomials. So we give a general name to a polynomial. So this is a random polynomial. And you're dividing it by x minus a, right? In this case here, we're dividing this thing by x plus 1. But you can say it's x minus negative 1. So when you divide it by x plus 1, then the a becomes negative 1. That will make it x plus 1. All right, so when you're dividing by x minus a, that's the remainder theorem says you have to make it minus here, until the remainder is a constant. In other words, you keep dividing until you get just a number as a remainder. Then there's a very quick way of finding the remainder. The remainder is, now watch this, this is f of a. In other words, what you do, here you got a, that's a there, the number you're dividing by. You take that number and you plug it into your original polynomial and simplify this. Once you give a value to x, you got a certain number, then it simplifies to get a number. That number is the remainder. So it's a very powerful thing. So you can find the remainder very, very quickly. Now let's take an example. Suppose I take 2x cubed minus x minus 4, and I divide it by x minus 3, right? Then according to this, the remainder is, the value for a here is 3. So you can put the 3 into this equation, and that will give you the remainder. That's what the remainder says. You take the 3 here, you put it into this, that'll give you the remainder. If you put 3 into this, 2 times 3 cubed is 2 times 27, which is 54, minus 3, which is 51. 51 minus 4 is 47. So the remainder is 47. Now, without even dividing, performing the long division, I know what the end result is going to be. The last line in the division problem will give you 47, right? But you can divide it. I actually divided it. When you divide x minus 3 into this, right? If you do it by long division, you get the quotient, and you will see that you have a remainder of 47. See, you get this the quotient, and that'll be the remainder. So this will take a much longer time than that. So bearing that in mind, you got x to the power of 51. You're dividing this by x plus 1. Then a is -1. Right? You got x plus 1. A is -1. You have to put -1 into this. And -1 to the power of 51, very easy to calculate. It is -1. -1 raised to any odd power is itself. But if you raise it to an even power, it's +1. -1 squared is +1. -1 cubed is -1, because you're multiplying -1 by itself 51 times. So you get -1, so 201 minus 1 is 200. Okay, guys. All right, I've actually given you a full lesson on something which is done maybe in grade 11 or in grade 12. It's called the remainder theorem. And you will do that. For the grade 10s, you have not seen it yet, but I've told you what the theorem is, and it's not difficult to understand what the theorem states. So now you know what the remainder theorem is. When you're dividing a polynomial by x minus a, you can calculate the remainder very easily by substituting the a into your polynomial. Substitute it, and that gives you the remainder. Right. And that's closely related to another thing called a factor theorem. And hopefully, when you have another problem, we'll come back to this thing. Okay, so let's get on to the next problem. I don't think any questions there, Shivar. They seem to be quite comfortable.
Yeah, I think they're all good, Prof.
Okay. All right, we've got to problem 17. We're making fairly good progress. A sporting club has 100 members. Of these 100 members, 44 play soccer, 45 play cricket, 65 play rugby, 8 play soccer and cricket only, 9 play rugby and cricket only. So a lot of information. And the question is now, the question is how many members play only rugby? It's a very good example of where a diagram can help you greatly. Now, when you got a problem like this, you use Venn diagrams, right? By Venn diagram, you mean you have two things which are sets. This A now becomes a set, and B becomes a set. These are not geometrical objects. This is not a circle. You don't think of a circle now. In a Venn diagram, this is a set, and this is a set, and it's got lots of objects inside it, right? Like what we've done here. So you can have object here, object here, object here. You can't see it, but normally you put in some stuff inside there, and inside here as well you put lots of objects, and then you say this is a set of a collection of objects. This is another set of collection of objects, and where they intersect like this, where they cut, these guys here is an object of A as well as an object of B. So these guys here are all in both in A and B, right? Both in A and B. And the symbol for that is A, and you put an upside down U like that, and B. Whenever you see this symbol, it means those objects which are in both A and B. And that's this picture here. If you look at these ones, which are outside this moon-shaped object, if you look at this, well, actually, this is also a moon-shaped object. If you look at this, these are the people who are in A, but they're not in B because it's outside B, you see? And so these are the objects which are in A and not in B. And likewise, these guys are the people who are in A and not in B, but not in A. Right? And if you take an object here outside, it means this guy is neither in A nor in B. He's out of the loop. He's out of the circle. Right? So this Venn diagram, it breaks up groups of sets into 4 pieces One is where both of them are in another one, it's in one of them and out from the other. And here you got it's in the other and out of the one. And here both of them are out. So this Venn diagrams can be very useful in problems like this. Now the actual problem is you got three things. You got soccer, cricket, and rugby. So you got three different sports. And for those three different sports, I have to draw three circles, as we see here in this diagram. Now last week, one of the learners, you know when we did the problem on carpets, right? We took those carpets and we made them circular carpets and we put them like this, and we solved the carpet problem like this. And the person made quite an interesting statement. He said, "But this looks like Venn diagrams." Of course, whoever it was quite right. Those carpets were like Venn diagrams, and there we saw in that context, we saw that this part here was where all three carpets were covered. Here, only two carpets were covered. Here, only one carpet was covered. So these all these different sections, you got nice descriptions for them in terms of the carpets. That was last week. But here now, in this thing here, we have description. Like for instance, all this here, all this. These are the people who play soccer, but they're out of rugby. They're not here, and they're also out of cricket. So these are the people who play soccer only. They don't play rugby, and they don't play cricket because they're outside here. See? And now here in this part here, these are the people who play soccer and rugby, but they don't play cricket. See? And here again, you got these people here, they play rugby and cricket. These people here, this region here, they play rugby, and they play cricket, but they're not in that one there. They're outside, so they don't play soccer. So like that now, you can take all the pieces of information which I've got here. 45 play soccer all together, right? 45 play cricket, 44 play soccer, 45 play cricket, and 50 play rugby. So we know what, when you say all together, it means all the people in this inside here, they all add up to 45, you see? 45 play soccer. And all these guys here, they all add up to rugby, which is 50. And all these, they add up to 45, they play cricket. Okay, now we take the information. They say 8 play soccer and cricket only. So you got soccer and cricket, and 8 falls inside here because they play soccer and cricket only. They don't play rugby. So therefore, I got an 8 here. Then you've got 9 play rugby and cricket only. So you got 9 here, like the previous case. And 7 play soccer and rugby only. Soccer, rugby, 7 here. So you can get the numbers 7, 8, and 9. That's the only information you've got. And of course, you've got how many people play soccer and how many people play cricket and how many play rugby, right? Then they say 5 play neither soccer, cricket, nor rugby. So there are people who are just the spectators who do not play any of these things, right? And there are 5. So that 5 comes outside the set. You can see the 5. I'll put it in here. All right. So now, how do you solve the problem? The question is, how many play all 3? So this is the thing. These are the people who play all 3, and we give a name to that. We want to solve for X, so we give a name to X. X members play all 3. Now, the moment you do that, then you got an X, you got a 7, you got an 8 here in these 3 pieces, and you know all together you're going to get how many? You got 44 play soccer. So 7, 8, and X will give you 15 plus X here. Right? 15 plus X here. And you want the whole thing, the total inside here, to be 44. So the part outside here will be 44 minus 15 plus X in brackets. And that gives you 44 minus 15 is 29. minus x. You can check. If you add up all these four numbers, minus x plus x gives you 0, 7, 29, and 8 gives you 29 plus 7 is 36 plus 8 is 44. The same way here, you'll have a minus x here, and these things add up to. This is rugby, so they must add up to 50. And this thing here, this outside part will be those who play cricket and do not play any of the other sports. So you have to add 17 and x and subtract it from 45 to get this. So now you filled in all the blanks. All these things have been filled. You got a 5 here and so on, right? And you use the final piece of information, which was that the club has got 100 members. So altogether, all the people in the club are inside this box here, outside, right? So this is a club here. I should have put down club here, outside. So you've got now, altogether you got 100. So you add up all these numbers together with the 5, and you will land up with, you should have 100, right? So in the next page, I'm adding up all these things together with the 5, and I'm saying that's 100. And you get a nice simple equation, 2x equals 20, x equals 10, right? Oh, but the question was actually, let's just get to this. How many members play rugby only, right? Not how many people play all three. I use a symbol for people who play all three. So my question is now, how many people play rugby only? I've got X, so I should be able to get everything else. X is, what did we say? 10. X is 10. And if you look at the rugby only, there's the rugby only here. These are the people who play only rugby, and we calculated that to be 34 minus X. So 34 minus 10 is 24. So there are 24 people who play rugby only. Very, very powerful strategy, Venn diagrams. When you got things like this, problems of this type, resort to Venn diagrams. Draw diagrams like this, and after that, it'll be quite easy. But you must just remember what each of those pieces are and give a description for it, and you would be on your way. All right. Is there anybody here who has got a question? Are you all okay? Who was the one who said those carpets looked like a Venn diagram? Put your hand up. They made a comment in the chat, which I thought was quite nice. All right. Maybe the person is shy or has forgotten that he or she asked that question in the carpet problem. Okay, going to problem number 18. How many odd positive integers, the sum of whose digits is 4, and none of whose digits is, yes? Yes, sure.
I think the person said.
Yeah, who was it? You put your hand up?
It's in the chat.
Oh, it's in
it
chat.
says 5-8.
Okay. Thanks for that comment last week. Pie Man. Hey, what's your real name? You give me a name as Pie Man. I don't know who you are. Okay. All right. So let's get back to this.
Prof, he said it was PS.
Who? What's his name? Okay.
He said PS or Pius.
Okay. I'll see that later. I'll see that later. All right.
Yeah.
Hey, you guys, you don't give me all your nicknames. Yeah, I've got your email addresses, and whenever you, I send emails to you, so you must give me your email address in your whenever you're talking to me, or give me your surname or something like that. Now, don't tell me, oh, this is Bobo. Right. I don't know who Bobo is. You must give me an identification which I can identify. All right. Let's get back to this question 18 here. How many odd positive integers? Positive, odd. 1, 3, 5, 7, so on. The sum of whose digits is 4. So when you're adding up the digits, you're going to get 4. And none of those digits is 0. Right? And how many of those are not prime? Yeah, these questions are quite, they test your understanding of language also, which can be problematical, but you have to just unpack the question. So what happens here is, you know, they are positive integers, so it could be anything like 10 million or whatever, that's a positive integer. But when you add the digits, you're going to get 4. And none of those digits is 0. So you're going to have 4, you're going to have numbers, positive numbers, which add up to 4. And they have to be odd numbers. Positive numbers whose digits add up to 4, they have to be odd numbers. That means the last number will have to be an odd number. And finally, those numbers should not be prime. Right? They must be prime numbers. They must be composite numbers. You must have factors for them. Right? And the question is, how many such numbers are there? So this is a counting problem again. But we don't have to count them. We can just list it like this now. You see, you can write 4 first. The issue is, you have to write 4 as a sum of numbers which is not equal to 0. So you got 4 equals 3 plus 1. You can have 2 plus 2. You have 2 plus 1 plus 1. 1 plus 1 plus 1 plus 1. Right? So your numbers can be 2, 1, 1, 2, 2, 1, 3, 1, 1, 1, or just 4 by itself. All right? Okay. Now, let's start from the bottom. If your numbers were all 1, so there's only one number, which is all 1. It's 1, 1, 1, 1. Okay, this is a number. When you add the digits, you're going to get 4. All right? By the way, these are the only ones. You can't have 5 summands here, because then you're going to get a 0 in it. You don't want a 0 in that number. You look at all these numbers, there's no 0 in it. Okay. Now, 2, 1, 1, you can add the numbers as 2 plus 1 plus 1, but there are 3 ways in which you can get 2, 1, 1. See, 211 is different from 121, which is different from 112. But in all those 3 cases, the numbers are 2, 1, and 1. Okay, so that takes care of the second group. And here, you want both the numbers to be 2. Okay, so there's only one number, 22, which is both the numbers 2. Here, you want one of the numbers to be 3 and the other number to be 1. There are 2 of them, 13 and 31. And then you've got this. That's the number 4. Now the question is, so you got a small finite collection of numbers which fit the bill, where they add up to 4, 1, 2, 3, 4, 5, 6, 7, 8. So the 8 numbers, where the sum is added to 4. Now we have to start eliminating. You want them to be odd. So they can end in 1, but you have to eliminate 1, 1, 2, 22, and 4. So that eliminates 3 things, because 2 of them finish with, 3 of them are even from the original 8 numbers. So you got 5 surviving. Right, now from this last lot, you want to know which of them are not prime numbers. Well, this one here, you can see quite quickly that this is 11 times 101. 11 goes into this. So this is a candidate. It is not a prime number. Right? I don't know how many of you know that 211 is a prime number, but we can come back to that. This is a prime number, by the way. And this thing here is not a prime number, so it's 11 times 11. 13, you all know is a prime number. And 31, you all know is a prime number. So there are only 2 candidates, 11, 11, and 1, 2, 1, which fit the bill, and the answer is 2. The only question is now, why is 211? How do you know that 211 is not a prime number? And you have to check this thing out. And to check it out, you have to try to factorize 211 I'm not going to use my text. Try to factorize 200. And you ask yourself, okay, which number is going to it? Certainly 2 doesn't go into it. 3 doesn't go into it because when you add the digits, you can get 4, right? 3 does not go into it. Now you can eliminate all the even numbers because 2 doesn't go into it. So you can go to the next one. 5 certainly doesn't go into it. 7, you can quickly try 7. 7 goes into this 21 times, out. 7 is out. 9 is out because the sum of the digits is not 9. 11, you try 11, it doesn't work. And the next one is 13. There you have to, 13 goes into 21 one time, and the remainder is 81. 13 does not go into 81. That we know. 81 is 9 times 9. But then you actually have to stop at 13 because 15 times 15 is 225. You see? So once you go up to 13, then you don't have to go beyond 15 times 15 because the moment you go beyond 15 times 15, you're going to have, like you try 17, then it means that the other factor will be smaller than 15. And we've just finished all the factors before 15. So you really need to just go up to the square root of your number if you want to find out what the factors are. You go below the square root. That's the general principle, right? And you can see that this is a prime number. So the answer is 2. All right. Okay, the next problem is a geometry problem. It says AB is the diameter of a circle. So this is the diameter. Remember earlier on, I told you when you got a diameter, if I take any point on the top and work out that angle, this angle will be 90 degrees. So that fact which I gave you earlier on, it's coming in useful here again. You may use this. This angle here is 90 degrees. This is also a point on the circumference. So if you start from one end and you go there, you go up there, you're going to get 90 degrees again, this angle here. Anyway, they say it's the diameter. Chord CD is parallel to AB. So this is parallel. MC, this is a radius. You can see there are 3 radii, MA, MC, and MB. They all must be equal because M is the center of the circle. It says M is the center. Yeah. So these are equal. In fact, if I join M to D, I'll get, that's also equal. That's a radius. That's also the radius at least. So it will be equal to all the other radii. All the radii are equal. But now they tell you that DE is a point such that AC equals EC. So you got AC equals EC. So these two are equal. That equals that. AC equals EC. And the problem is to find the angle CAM. This angle here in degrees. They don't give you any angle here, rascals. They only tell you all these different sides are equal. But you evidently will have to use isosceles triangles, have got the